We continue Unit 3, Inverses, with flap 6 in our foldable, verifying inverses. There are two ways to determine if two functions are inverses of each other, graphically and algebraically. When two functions are inverses of each other, they are reflections across the line y equals x. Algebraically, we can use composite functions to determine if two functions are inverses of each other. Let's look at example 1. Determine both algebraically and graphically whether or not f and g are inverse functions. To begin, let's look at f of g of x. From yesterday's lesson, we start with the outside function f and we substitute g of x in place of x. Now, anywhere I see an x in f, I'm going to replace 1/4 x minus 3. So let's write down the function 4 times x plus 3. Remember, this is my new x, 1/4 x minus 3. Now distribute. 4 times a fourth, x, is just equal to x. 4 times negative 3 is negative 12 plus 3. And this is equal to x minus 9. Since x minus 9 is not equal to x, then I stop. This, f of x equals 4x plus 3, and g of x equals 1/4 x minus 3 are not inverses. So to recap, we use composite functions. We start with f of g of x is equal to x, and g of f of x is equal to x. If both of them are equal to x, then these two would be inverses of each other. Starting with f of g of x, I substitute g of x in for f. Then we simplify. If our answer is not x, then we can stop because these are not inverses. Now the directions say to show both graphically and algebraically. We have just shown algebraically that they are not inverses of each other. So now let's look at the graph. Go ahead and draw line y equals x first. Now let's plot 4x plus 3. Remember, b is the beginning ordered pair. It's where it crosses the y-axis, and the slope is m, which is 4 over 1. So I'll plot the beginning ordered pair, 3, on the y-axis, and then the rise over run is 4 over 1. So this is line y equals 4x plus 3. Make sure and name your line. Then 1/4 x minus 3, let's graph that in red. The y-intercept is b. The slope is 1 over 4, and it's positive. So b is negative 3. Rise is 1. Run is 4. And label this graph. You can see that these table values are not reflections of each other. If this was a reflection, this 0.03 would have been 30, and it's not. So you can easily see graphically that they are not reflections across the line y equals x. So therefore, graphically, I have shown that these are not inverses of each other, these two functions. Let's look at another example. Let's show algebraically that these are inverses of each other or they are not. To do this, we will do the composite function. Since this is starting with f, I will say f of g of x. Starting with the outside function, anywhere I have an x in f, I'm going to plug g in. So let's leave a blank where g of x would be. And g of x is 1/3 x minus 2. Now we distribute 3 throughout the function. So 3 times 1/3 x is equal to x. 3 times negative 2 is negative 6 plus 6. And when we combine like terms, we just get x. Because I got x, I need to verify that this one also works, because it has to work with both. So now I have g of f of x, which means anywhere I have an x in g, I'm going to replace it with f of x. So write the function for g, leaving a blank for x. And in that blank, we are going to put f of x. What is f of x? It is 3x plus 6. Distribute 1/3 through the parentheses. 1/3 of 3 is 1x. 1/3 of 6 is plus 2. And then minus 2. Combining like terms, and we get x. Because both f of g of x and g of f of x result in x, these two functions are inverses of each other. Now let's prove that these two are inverses of each other graphically. Let's start by plotting y equals x. Now let's plot f of x. Now let's graph the second equation. Now remember, for these to be inverses of each other, the x and y values are switched. If I take the easiest point to see, the ones on the y-intercept, 0 up 6, then on the other graph it should be 6, 0. And it is. Look at the next one, -1 up 3, so we should see 3, -1. -2, 0, 0, -2. So you can easily see that these points are reflections of each other across the line y equals x. Therefore, these two functions are inverses of each other, and we have shown both algebraically and graphically that they are. Two more examples. Now let's determine algebraically if the two functions are inverses. We're going to use composite functions to show this. F of g of x. Anywhere I see an x in f, I'm going to replace it with g of x. So start with the outside function, write that function, leaving a blank where x is. This is where we're going to substitute g of x. Now g of x is 1 over 2 x minus 2. Distribute 2 through the parentheses. 2 times a half is 1x. 2 times -2 is -4, and then plus 4. And when we combine like terms, we get x. Because I get x, I need to also check the other one to verify. So this time I'm going to do g of f of x. And everywhere I have an x in g, I'm going to leave blank. So 1/2 times blank minus 2. And we will substitute f of x into this spot. Distribute 1/2 through the parentheses. 1/2 of 2 is 1x. 1/2 of 4 is 2 minus 2. Combine like terms, and you get x. That's it. Since f of g of x is equal to x, and g of f of x is equal to x, these two are inverses. So we have verified it. Okay, let's verify that these two are inverses. Let's start with f of g of x. So everywhere I see an x in f, I'm going to replace it with g. So write the equation for f, leaving a blank where there's an x. Now substitute g of x. Last thing is to simplify. The 5's will reduce to 1, leaving 2x minus 3 plus 3 over 2. Combining like terms, leaving 2x over 2, which is just x. Now let's look at g of f of x. Now writing the equation for g, anywhere we have an x in g, we want to leave a blank. Now substitute f of x in for the blank. F of x is 5x plus 3 divided by 2. Now simplify, and the 2's will reduce, leaving 5x plus 3 minus 3 over 5. Combining like terms, the 3's go away, leaving 5x divided by 5. 5 goes into 5 one time, leaving x. So yes, these are inverses of each other. And this concludes verifying inverses.